Before fuel injection took over, carburetors were the beating heart of every internal combustion engine. Engineers spent decades perfecting these mechanical marvels, creating ingenious designs that mixed air and fuel with stunning precision. Some were so advanced they seemed like pure wizardry. But when electronic fuel injection arrived, these brilliant designs vanished almost overnight. If you love automotive innovation and engineering genius, hit that subscribe button right now because we're diving into 20 carburetor designs that were absolute game changers but got left behind when the digital age took over. Let's start with the Rochester Quadra Jet. This thing was a monster on American muscle cars throughout the 70s and 80s. What made it special was its split personality. It had tiny primary bores for smooth cruising and fuel economy, then massive secondary bores that opened up when you stomped the gas. The spread bore design was pure genius because it gave you the best of both worlds. Daily driving felt refined and economical, but punch it and those secondaries would open up like floodgates. GM put these on everything from Corvettes to pickup trucks. The engineering was complex with air valves that opened based on engine demand rather than just throttle position. When fuel injection came along, computers could manage this split personality electronically, making the mechanical complexity obsolete. Next up is the SU carburetor from Britain. These were all over British sports cars like MGs, Triumphs, and Jaguars. The SU used a sliding piston with a tapered needle that moved up and down to regulate fuel flow. As the piston rose with increased airflow, the needle pulled out of a jet, allowing more fuel through. The beauty was in its simplicity and how it automatically adjusted the mixture across the entire RPM range. Tuning required balancing multiple carbs with a special tool to sync them perfectly. Mechanics who mastered SU carbs were like artists. The constant velocity design meant smoother power delivery than most other carburetors. But that mechanical piston and spring setup couldn't compete with the precision of electronic sensors constantly adjusting fuel delivery thousands of times per second. The Weber DCOE is legendary among performance enthusiasts. But these Italian side-draft carburetors were the weapon of choice for racing engines worldwide. Each cylinder could get its own choke, making them incredibly responsive. The horizontal mounting meant shorter intake runners for better throttle response. Tuning a set of Weber DCOEs was an art form with jets, emulsion tubes, air correctors, and accelerator pumps all working together. Getting 4 or 6 of these synchronized was a nightmare, but when dialed in perfectly, the throttle response was instantaneous, and the sound of those trumpets sucking air was intoxicating. Race teams spent hours jetting these for different tracks and conditions. Modern fuel injection does all that adjustment automatically in milliseconds, which is why you don't see Webers anymore except on vintage racing machines. The Holley double pumper changed drag racing forever. Unlike normal carbs with vacuum-operated secondaries, the double pumper had mechanical linkage that opened all 4 barrels simultaneously when you floored it. It also had 2 accelerator pumps instead of 1, shooting massive amounts of fuel into the engine the instant you hit the throttle. This eliminated any hesitation or bog off the line. Drag racers loved them because they delivered fuel now without waiting for vacuum signals. You could literally hear those pumps squirting fuel into the Venturas. The trade-off was terrible fuel economy and drivability in normal conditions, but who cared when you were launching hard at the strip? Electronic fuel injection can now dump fuel even faster with better precision, making these mechanical fuel cannons unnecessary. Solex carburetors dominated European cars for decades. French engineering at its finest, these carbs used a complex system of jets and air bleeds to achieve precise fuel metering. The downdraft design worked beautifully with European engine layouts. What made Solex special was the progressive secondary system that gradually opened rather than suddenly dumping fuel. This made for smooth power delivery that matched the character of European cars. Volkswagen Beetles used Solex carbs for years with bulletproof reliability. The casting quality and attention to detail in manufacturing was exceptional. Rebuilding a Solex revealed just how much thought went into every passage and jet. But all that precision machining and hand-tuning became pointless when a $20 oxygen sensor could tell a computer exactly what the engine needed. But Carter Thermoquad carburetors were space-age technology in the 70s. The entire main body was made from phenolic resin, a plastic composite that kept fuel cooler and reduced vapor lock. These massive carbs flowed incredible amounts of air through huge secondary bores while maintaining excellent fuel economy on the small primaries. The plastic construction made them lightweight compared to aluminum or zinc carbs. Chrysler put them on everything from station wagons to muscle cars. The problem was the plastic could warp if someone tried to over-tighten bolts or if the engine ran too hot. Tuners initially distrusted the plastic, but once they understood the design, these became highly sought after. The fuel economy gains were real and measurable. Still, even innovative materials couldn't save carburetors once computers proved they could optimize fuel delivery better than any mechanical device. Mikuni carburetors ruled the motorcycle world for generations. Japanese engineering created these perfectly tuned instruments that made motorcycles run like Swiss watches. The constant velocity design with a vacuum-operated slide gave smooth power delivery that matched motorcycle riding perfectly. The accelerator pump was tiny but perfectly calibrated for quick blips of the throttle. Mikuni made thousands of variations for different bikes, each one specifically jetted and calibrated for that particular engine. Motorcycle mechanics became experts at rejetting Mikunis for altitude, temperature, and modifications. And the diaphragm in the slide needed occasional replacement, but otherwise these things ran forever. When fuel injection came to motorcycles in the 90s, riders initially resisted because they loved the mechanical connection and tunability of Mikunis. Now even vintage bike owners are switching to modern EFI systems. The Stromberg carburetor was another British classic that used a constant depression principle similar to SUS, but with its own clever design variations. These showed up on everything from Saabs to Volvos to British Leyland cars. The air valve design automatically compensated for air density changes with altitude and temperature. American versions were built under license and used extensively by Ford. The WW series Strombergs were especially popular because they were simpler to tune than SUS, while still providing excellent drivability. Cold starting enrichment was handled by a temperature-sensitive spring mechanism that gradually leaned out the mixture as the engine warmed. This mechanical thermostat was ingenious for its time. Emissions regulations in the 70s made these carbs increasingly complex with additional vacuum-operated systems. Eventually, the band-aids and complications made fuel injection the cleaner, simpler solution, despite being more expensive initially. Zenith carburetors were the go-to choice for many American cars in the early 20th century. These pioneering designs established many principles that later carburetors would refine. The updraft design pulled air upward through the venturi, which worked well with early engine layouts. As cars evolved, Zenith adapted with downdraft and sidedraft versions. The Zenith Stromberg division later merged technologies, creating hybrids of both design philosophies. Military vehicles used Zenith carbs extensively because of their reliability and ease of maintenance in field conditions. The simple construction meant a mechanic could rebuild one with basic tools and a parts kit. During World War II, thousands of Jeeps and trucks ran Zenith carbs through deserts, jungles, and frozen tundra. That kind of mechanical reliability was crucial before electronics became rugged enough for military use. The Keihin carburetor became synonymous with Honda reliability. These Japanese carbs were engineered to incredibly tight tolerances with quality control that was obsessive. The Honda engines were famous for running perfectly for hundreds of thousands of miles, and the Keihin carbs were a big part of that reputation. The accelerator pump timing was calibrated to eliminate any flat spots in throttle response. Cold starting systems worked flawlessly even in harsh conditions. The automatic choke used a bimetallic spring that was perfectly calibrated to engine temperature. Tuners found that Keihin jetting was so precise that changing jets in half sizes made noticeable differences in performance. When Honda started switching to fuel injection in the 80s, the transition was gradual because their carburetors already worked so well that customers didn't immediately see the benefit of the new technology. Rochester Varajet carburetors were GM's answer to increasingly strict fuel economy standards in the late 70s. These small two-barrel carbs used variable venturi technology where the venturi size changed based on engine demand. At idle and cruise, the venturi was tiny for maximum fuel economy. Under acceleration, it opened wider for more airflow. The design was clever, but complex, with lots of small moving parts. Feedback systems connected to early oxygen sensors tried to maintain ideal air-fuel ratios. These were some of the first carburetors with electronic control systems, making them a bridge technology between pure mechanical carbs and full fuel injection. The complexity made them difficult to service, and many mechanics simply replaced them with simpler carbs. Ironically, and all that complexity was trying to achieve what fuel injection would do better just a few years later. The Amal carburetor was the heart of British motorcycles for decades. Norton, BSA, and Triumph bikes all relied on these simple, elegant designs. The concentric model with its central float bowl became iconic. The tickler button on top let you manually flood the float bowl for cold starting, a very British solution that actually worked quite well. Racing versions had remote float bowls and clip-on tuning jets that could be changed between races without disassembly. The Amal concentric was so perfectly suited to parallel twin engines that even today vintage bike enthusiasts insist nothing sounds or runs quite like a properly tuned Amal. The company still exists, making carbs for vintage restorations and classic racing. But modern bikes have moved on, but the Amal represents a time when motorcycles were simple mechanical art that connected rider to machine. Dellorto carburetors were Italian racing technology that eventually made it to street bikes. Ducati used these extensively, and the screaming sound of a Ducati with Dellorto carbs is unforgettable. The PHM series became legendary for ultra-responsive throttle and race-proven reliability. Accelerator pumps were adjustable with different cam profiles to tune the exact moment and amount of fuel squirted during throttle transitions. Slide-type Dellortos gave even sharper response than CV carbs. Setting the float height required precision because even a millimeter made a noticeable difference in mixture. But Italian superbikes, in the 80s and 90s, were often carbureted long after Japanese bikes went to fuel injection because engineers felt they could extract more peak performance from properly tuned Dellortos. Eventually, emissions regulations made that position impossible to defend. The Bing carburetor came from Germany and powered BMW motorcycles for generations. These constant velocity carbs were engineered with typical German precision. Every passage was carefully sized and every component built to last. BMW Boxers ran Bing carbs for decades with legendary reliability. The side-mounted float bowls were positioned to prevent fuel starvation during hard cornering. Altitude compensation was built in so bikes performed consistently from sea level to mountain passes. A Bing also supplied carbs for Rotax engines used in various applications. The quality of castings and materials meant these carbs lasted as long as the engines they fed. Rebuilding a Bing decades later, you could still see sharp, crisp edges in the castings with no wear. When BMW finally switched to fuel injection, it was purely for emissions compliance because the Bing carbs were still running perfectly. Carter. AFB carburetors were lightweight aluminum 4-barrels that competed directly with Holley on American performance cars. The AFB stood for aluminum 4-barrel, and these carbs saved significant weight compared to cast-iron designs. Chrysler and American Motors used them extensively. The secondary air valve design opened progressively based on airflow demand, making them more street-friendly than mechanical secondary carbs. And Edelbrock later bought the design and still manufactures updated versions today as the Performer series. The simplicity of the design made them reliable and easy to rebuild. Racing versions had all the adjustability serious tuners needed. The casting quality was excellent with smooth ports and careful attention to airflow. These carbs proved that good engineering and quality manufacturing created products that outlasted their original applications. The Ford Autolite carburetor was engineered specifically for Ford engines, and the integration showed. These carbs knew exactly what Ford 5.8S needed and delivered it efficiently. The 2-barrel versions were bulletproof reliable on millions of trucks and cars. 4-barrel versions powered Mustangs and Fairlanes through the muscle car era. And the load-sensing design used a diaphragm connected to intake manifold vacuum to adjust fuel delivery based on engine load. This primitive form of feedback control improved both performance and economy. Ford kept refining these carbs through the 70s with increasingly complex vacuum-operated systems for emissions control. By the early 80s, there were so many vacuum lines and solenoids that the carburetor itself was almost invisible under all the emission equipment. Fuel injection finally eliminated that complexity. The Marvel Schebler carburetor went back to the earliest days of aviation and automotive engines. These primitive but effective designs used a simple float and needle valve system that established principles still used a century later. Tractors and farm equipment used Marvel Schebler carbs for decades because of their simplicity and reliability. A farmer could clean and rebuild one in a barn with basic tools. The updraft design kept dirt and debris from falling into the venturi. Many industrial engines ran these carbs for 50 years or more with minimal maintenance. The company name became shortened to just Schebler over time. While primitive by later standards, these carbs worked reliably in conditions that would kill more sophisticated designs. Sometimes simple is better, but eventually even farm equipment needed to meet emission standards that required electronic control. Solex ADDHE carburetors represented the peak of mechanical fuel metering before electronics took over. These complex units had multiple progression circuits, accelerator pumps, and enrichment systems all working together. European performance cars used them to extract maximum power while still meeting increasingly strict regulations. The engineering inside was mind-boggling with dozens of precisely sized jets and passages. Air correction jets compensated for the fact that air and fuel have different densities at different flow rates. Emulsion tubes mixed air with fuel before it entered the venturi to improve atomization. All this happened purely through mechanical means, using airflow and vacuum as control signals. Tuning required understanding fluid dynamics and thermodynamics. When computers could measure actual oxygen content in exhaust and adjust fuel delivery in real time, even these sophisticated mechanical systems became obsolete overnight. The Hitachi carburetor powered Datsun and Nissan vehicles through their rise to prominence in American markets. These carbs were reliable, efficient, and well-matched to Nissan engines. The automatic choke systems worked flawlessly in all climates. Secondary systems opened smoothly for good acceleration without harshness. Nissan engineers calibrated everything for the specific characteristics of their engines, including cam timing, compression ratios, and exhaust systems. This holistic approach made the entire package work better than the sum of its parts. As Nissan moved upmarket in the 80s with the 300ZX and other performance models, they were early adopters of fuel injection technology. The switch improved performance and economy simultaneously, showing clearly that the carburetor era was ending. Still, millions of older Nissan vehicles ran Hitachi carbs for decades afterward, proving the basic design was fundamentally sound. The legacy of these ingenious carburetor designs lives on in the engineers who created them and the enthusiasts who still rebuild and tune them today. Each design represented the cutting edge of technology for its time. Engineers used fluid dynamics, metallurgy, and precision manufacturing to create devices that could reliably meter fuel across enormous ranges of airflow, temperature, and pressure using only mechanical means. No electricity required, no computers needed, just perfectly calibrated springs, jets, and passages doing exactly what physics demanded. Modern fuel injection is undeniably superior in every measurable way. But there was an elegance to solving complex problems with purely mechanical solutions. These 20 carburetor designs disappeared not because they failed, but because technology moved forward. They deserve to be remembered as the ingenious solutions they were, bridging the gap between the earliest primitive engines and the computer-controlled power plants we have today. There's something almost poetic about how quickly these mechanical marvels vanished from the automotive landscape. One day, carburetor tuning was a respected skill that could make or break an engine's performance, and the next day, that knowledge seemed completely irrelevant. But here's the thing that's really important to understand. Those engineers weren't wrong. They weren't building inferior technology. They were pushing the absolute limits of what was mechanically possible. They were solving incredibly complex problems with nothing but steel, aluminum, and brilliant design thinking. The fact that they succeeded as well as they did makes their eventual obsolescence even more impressive in a strange way. They proved that mechanical engineering could handle tasks we thought required electronics. If you're someone who's ever spent time rebuilding a carburetor, you know exactly what I mean. You're holding a piece of metal with dozens of precisely sized passages, looking at jets measured in fractions of a millimeter, and wondering how anyone figured out those exact dimensions without computer modeling or flow benches. The answer is that they tested and refined and failed and tried again for years. They understood fluid dynamics intuitively because they had to. They couldn't just run a simulation and see the answer pop up on a screen. They had to think it through, build it, test it, measure it, and then start over. That process created engineers with a deep, fundamental understanding of how engines actually work. What's fascinating is that fuel injection technology actually needed those carburetor engineers to pave the way. The fundamental principles of metering fuel, understanding air velocity, managing enrichment cycles, and controlling acceleration didn't change. What changed was the control mechanism. Instead of a mechanical spring pulling a needle out of a jet, you have a solenoid pulse width modulating an injector. Instead of vacuum signals and air valves, you have oxygen sensors and computers. The physics remained identical. The carburetor guys figured out what needed to happen, and the fuel injection guys figured out a better way to make it happen. And every fuel injection system owes an intellectual debt to decades of carburetor development. The transition period was actually really interesting if you look at it closely. During the late 70s and early 80s, you had this weird hybrid period where carburetors were getting computer controls added to them. Oxygen sensors fed data to simple computers that would adjust mixture with solenoid-operated vacuum valves. Some of the latest carburetors had more electronics than the first generation of fuel injection systems. It was this awkward middle ground where engineers were trying to squeeze better performance and emissions out of mechanical designs by adding electronic controls. But it became obvious pretty quickly that if you were going to use electronics anyway, why keep the mechanical complexity at all? Just inject the fuel directly into the cylinder and eliminate the carburetor altogether. Those late-model carburetors with electronic controls are actually really underappreciated by the collector community. They represent the moment when mechanical engineering admitted it needed help from electrical engineering. Some of them worked remarkably well despite the awkwardness of the hybrid approach. The feedback carburetors that tried to maintain stoichiometric mixtures using oxygen sensors were genuinely clever. They weren't as good as the fuel injection systems that came right after them, but they were way better than earlier carburetors, and they proved the concept worked. Some of those systems are still running today on older vehicles, still doing their job after 40 years. That's testament to the quality of engineering that went into them, even as the industry was moving in a different direction. What really strikes me is how quickly the knowledge disappeared. There are probably millions of people under 40 who have never even seen a carburetor, let alone know how to tune one. The skill set that was absolutely essential to being a mechanic just 30 or 40 years ago is now completely foreign to most people working on cars today. If you handed a modern fuel injection technician a worn-out carburetor and asked them to diagnose a rich condition, they might not even know where to start. The training schools stopped teaching carburetor theory, the service bulletins stopped being published, and the shops stopped stocking jets and gaskets. Within maybe 10 years of fuel injection becoming standard, the institutional knowledge of how to work on carburetors almost completely evaporated from the mainstream automotive industry. But here's the beautiful part. It didn't completely disappear. The vintage car community, the hot rodding world, and the motorcycle restoration scene all kept the knowledge alive. There are still people who can look at a carburetor and tell you exactly what's wrong with it just by the way the engine runs. There are still shops that specialize in rebuilding and tuning carburetors for classic cars and race engines. The knowledge had to get niche and specialized, but it survived. It survived because there were people passionate enough about vehicles to care about understanding how they work, not just accepting that they work. And those people decided that the elegance of a properly tuned carburetor was worth keeping alive even when modern alternatives were available. That's a form of respect for engineering history that I think is really important. The carburetor might be gone from new cars, but its influence is everywhere in how we engineer fuel delivery systems today. The principles of progressive metering, acceleration enrichment, cold start procedures, and load sensing are still there in the code that runs modern engines. The engineers writing that code learned it from the carburetor guys who figured it out decades ago. Every time a computer in a modern car adjusts fuel delivery, it's following a script that was written by mechanical engineers who had to solve these problems without electronics. That's a fascinating chain of knowledge connecting the simplex carburetors of the 1920s directly to the latest hybrid engines of today. You can't fully understand modern fuel management without understanding where it came from. If you think about it, the story of carburetors is really the story of how human engineering evolves. We solve problems with the tools we have available. When we only had mechanical tools, we became incredibly creative and sophisticated in how we use them. When electronics became available, we switched to those tools because they let us solve the same problems better. But that doesn't invalidate the earlier solutions. A perfectly tuned Weber DCOE carburetor flowing air through a small block Chevy is still one of the most beautiful examples of mechanical engineering and pure automotive fun you can experience. The fact that fuel injection is more efficient doesn't make that any less true. Different tools, different eras, same fundamental desire to make engines run better. This is actually why I love automotive history so much. Every technology tells a story about what was possible at that moment in time and what engineers prioritized. Carburetors prioritized simplicity in operation with mechanical complexity hidden inside. Fuel injection prioritizes mechanical simplicity through electronic complexity. Both approaches reveal something about the engineering culture of their era. Neither is universally superior in every way. Carburetors are lighter, cheaper to manufacture, don't require electricity, and can be tuned with simple hand tools. Fuel injection is more efficient, more responsive, cleaner, and more reliable across extreme conditions. They're optimized for different values and different constraints. Understanding that helps you appreciate why each technology existed and why it eventually gave way to the next one. The beautiful thing about technology history is that older doesn't always mean worse and newer doesn't always mean better. It just means different. It means adapted to different circumstances, different regulations, different customer priorities, and different manufacturing capabilities. A 1968 Holley double pumper wasn't inferior to a 1988 electronic fuel injection system because they were solving slightly different problems with slightly different constraints. By 1988, you had environmental regulations that made fuel injection necessary. You had customers who wanted better cold starts and hot starts and altitude compensation. You had manufacturers who wanted better diagnostics and warranty tracking. None of those pressures existed in 1968 when the double pumper was state-of-the-art. So respecting carburetor engineering means understanding it in its own context, not judging it by modern standards. Thank you so much for sticking with me through this dive into carburetor history. If you found these mechanical engineering stories fascinating, please hit that subscribe button so you don't miss the next exploration into forgotten technology and engineering brilliance. There are so many amazing stories about incredible machines that shaped how we get around today. Why don't you leave a comment and tell me which carburetor fascinated you the most, or share your own experiences rebuilding or tuning these mechanical marvels. And if you happen to own a vehicle with an original carburetor, take a moment to appreciate the ingenious engineering that's sitting right there in your engine bay. Those aren't relics of inferior technology. They're monuments to what human creativity could accomplish with mechanical solutions to complex problems. Thanks for watching, and we'll see you on the next one.